Advanced substitutions. Recall that the substitution rule tells us that integral of f evaluated at g of x times g prime of x dx is integral of fu du, where we have used a substitution u equals g of x, and then du is g prime of x dx. Substitution is a method to rewrite integrals in simpler forms. With a correct substitution, we may be able to rewrite an integral in a form which can be evaluated just by looking at the table of integrals. But finding this correct substitution is often difficult. There are, however, certain types of integrands for which we have general methods. And here we discuss three such basic examples. Examples to be considered are, first, integral of square root of 1 minus x squared dx, and we compute this by the substitution x equals sine of u. When we do that, then 1 minus x squared is 1 minus sine squared, which is cosine squared, and square root of that can be simplified. Second example is integral of square root of 1 plus x squared dx, and here we use the hyperbolic substitution x equals hyperbolic sine of u. Because in this case, then 1 plus x squared becomes 1 plus hyperbolic sine squared of u, which simplifies to hyperbolic cosine squared of u, and square root of that is simply hyperbolic cosine of u. The third example is integral dx divided by square root of x plus cube root of x. And here we use the substitution x equals u to the power 6. When we do that, then square root of x becomes just u cubed, and cube root of x becomes u squared. Therefore, this substitution allows us to get rid of the roots in the integrand, and therefore it works. In this example, we compute the integral of square root of 1 minus x squared dx, and we do that by the substitution x equals sine of u. When x is sine of u, then dx is cosine of u du. Square root of 1 minus x squared is defined if 1 minus x squared is non-negative. This means that x must be between -1 and 1. And therefore, we may restrict the domain of definition of u to be the interval from negative pi over 2 to pi over 2. Because if u is negative pi over 2, then sine of u is just -1. And as u grows to pi over 2, sine of u grows from -1 to 1. In this interval between negative pi over 2 and pi over 2, cosine of u is non-negative. So when we compute the integral of square root of 1 minus x squared dx, with this substitution we get first integral of square root of 1 minus sine squared of u times cosine of u du. But now this square root of 1 minus sine squared is square root of cosine squared. And since we assume that cosine is non-negative, then square root of cosine squared is cosine itself. And this means that the integral now becomes integral of cosine squared of u du. Next, we have to compute the integral of cosine squared of u du. And in order to do that, we recall that cosine squared of u is cosine at 2u plus 1 divided by 2. This is the double angle formula for the cosine function. Therefore, the integral of cosine squared of u du is the same as the integral of cosine at 2u plus 1 divided by 2 du. This is now easy to evaluate. To be precise, one might want to do still an additional substitution, which would be 2u equals a new variable t. But that can be done without actually writing it down, and we get that antiderivative of cosine 2u divided by 2 is 1/4 sine of 2u. And then antiderivative of 1/2 is just u over 2. So we get that the integral of square root of 1 minus x squared dx is now 1/4 sine of 2u plus u over 2 plus constant of integration c. So here u equals sine of u. How to get back to the original variable x? We had the result that the integral of square root of 1 minus x squared dx is 1/4 sine of 2 times u plus u over 2 plus c. And x is sine of u. In order to get back to the original variable, we still have to do some more work. In order to rewrite the answer, integral square root of 1 minus x squared dx equals 1/4 sine of 2u plus u over 2 plus constant of integration c. In terms of x, we first observe that sine of 2 times u is 2 times sine of u times cosine of u. So 1/4 sine of 2 times u is just 1/2 sine of u times cosine of u by the double angle formula for sine. And then we still had in our answer the terms u over 2 plus constant of integration c. Now cosine of u is square root of 1 minus sine squared. We had restricted the interval of u to be from negative pi over 2 to pi over 2, then cosine is non-negative. And we get that this integral of square root of 1 minus x squared dx is 1/2 sine of u times square root 1 minus sine squared of u plus u divided by 2 plus constant of integration. And in this answer, sine of u is x. And we may now replace sine of u with x, and u has to be replaced by arc sine of x. We get that integral of square root of 1 minus x squared dx is 1/2 x square root 1 minus x squared plus arc sine of x divided by 2 plus constant of integration. And this is our answer. Integral of square root of 1 minus x squared dx is 1/2 x square root 1 minus x squared plus arc sine of x divided by 2 plus constant of integration. By a substitution, we got that integral of square root of 1 minus x squared dx is 1/2 x square root 1 minus x squared plus arc sine of x divided by 2 plus the constant of integration c. This formula can be derived also alternatively. The alternate solution uses the fundamental theorem of calculus. The fundamental theorem of calculus states that an antiderivative of the function square root of 1 minus x squared can be obtained by the definite integral from 0 to x square root of 1 minus t squared dt. So we conclude that the indefinite integral of square root of 1 minus x squared dx is the definite integral from 0 to x square root of 1 minus t squared dt plus a constant of integration c. This definite integral on the right-hand side can be computed by interpreting it as an area, and then we compute that area. The definite integral from 0 to x of square root of 1 minus t squared dt is the area of the colored domain under the graph of the function square root of 1 minus t squared and over the interval from 0 to x. Here the horizontal axis is the t-axis. X is a number on that t-axis, and we look at the domain over the interval from 0 to x and under the graph of the function square root of 1 minus t squared. The graph of that function is the upper half of a circle of radius 1 with center at the origin. It is the blue curve indicated here in this picture. We split this domain into a right angle triangle and to a sector of the disk, as indicated here in this picture. The right angle triangle in this picture has horizontal leg of length x. Its vertical leg is of length square root of 1 minus x squared, just by the definition. The area of a triangle is base times height divided by 2. So the area of this right angle triangle in this picture is 1/2 x square root of 1 minus x squared. This is the first term in the formula for the integral of square root of 1 minus x squared dx. Next we have to compute the area of the sector indicated here in this picture. To that end, we have to compute the angle of the sector, and we observe that that angle is the same as the acute angle indicated here in this right angle triangle. So the two angles alpha in this picture are the same. Now the right angle triangle has hypotenusa of length 1, because the blue curve is an arc on the circle of radius 1. So we observe that sine of alpha, just by looking at this right angle triangle on the picture and the rightmost alpha in the picture, sine of alpha is x divided by 1. So sine of alpha is simply x, and this means that alpha is arcsine of x. And now the area of an angle alpha sector of a disk of radius 1 is just alpha over 2. It can be computed by the formula, which is the angle of the sector, in this case it is alpha, divided by the full angle, which is 2 pi, times the area of the disk, which is pi times radius squared. Now radius is 1, so we get the angle alpha divided by 2 pi times pi, which simplifies to alpha over 2. And alpha is arcsine of x, so we get that the area of this sector indicated in this picture, the colored pink sector of the disk, is arcsine of x divided by 2, and this is the second term in the formula for the integral of square root of 1 minus x squared dx. The conclusion of this geometric argument is that integral from 0 to x square root of 1 minus t squared dt, which is the area of the pink domain in the picture, is the area of the triangle plus the area of the sector, and that is 1/2 x square root 1 minus x squared plus arcsine of x divided by 2. Here we have assumed that x is positive, but the same result holds, and the same argument also holds if x is negative. By the fundamental theorem of calculus, we had observed that integral of square root of 1 minus x squared dx is the definite integral from 0 to x square root of 1 minus t squared dt plus constant of integration. And we computed the definite integral from 0 to x square root 1 minus t squared dt by computing the area of the pink domain, and we got that this is 1/2 x square root 1 minus x squared plus arcsine of x divided by 2 plus then constant of integration c. So the result is of course the same as the one obtained by the substitution x equals sine of u. For the next example, recall that hyperbolic sine of x is e to the x minus e to the negative of x divided by 2, and that hyperbolic cosine of x is e to the x plus e to the negative of x divided by 2. Straightforward differentiation implies that derivative of hyperbolic sine is hyperbolic cosine, and that the derivative of hyperbolic cosine is hyperbolic sine. Furthermore, by computing with these definitions, we easily observe that hyperbolic cosine squared of x minus hyperbolic sine squared of x is 1. This means that hyperbolic cosine squared of x is 1 plus hyperbolic sine squared of x. Furthermore, we have that hyperbolic cosine squared of x is hyperbolic cosine at 2x plus 1 divided by 2, and that hyperbolic sine at 2x is 2 times hyperbolic sine at x times hyperbolic cosine at x. So these formula are similar to the formula that the trigonometric functions satisfy. There are some differences, however, and this means that these hyperbolic substitutions can be used to compute certain integrals where the trigonometric substitutions do not work. To compute the integral of square root of 1 plus x squared dx, we use a hyperbolic substitution, x equals hyperbolic sine of u, then dx is hyperbolic cosine of u du. If we perform this substitution, then integral of square root of 1 plus x squared dx becomes integral of square root of 1 plus hyperbolic sine squared of u times hyperbolic cosine u du. 1 plus hyperbolic sine squared of u is simply hyperbolic cosine squared of u. Square root of that is hyperbolic cosine of u. So we observe that this integral became integral of hyperbolic cosine of u times hyperbolic cosine of u du, which is just integral of hyperbolic cosine squared of u du. To compute this last integral, we recall that hyperbolic cosine squared of u is hyperbolic cosine at 2 times u plus 1 divided by 2. This is the double angle formula for hyperbolic cosine function. Therefore, integral of hyperbolic cosine squared of u du is integral of hyperbolic cosine at 2 times u plus 1 divided by 2 du. This last integral is easy to compute. We may perform the additional substitution that 2 times u is a new variable t, and we get the result in this way. The result is that integral of hyperbolic cosine squared of u du is 1/4 hyperbolic sine at 2 times u plus u over 2 plus constant of integration. This is now our answer for the integral of square root of 1 plus x squared dx. It is 1/4 hyperbolic sine of 2 times u plus u over 2 plus constant of integration c. But we wish to express the result in terms of the original variable x, which was hyperbolic sine of u. So the question is now how to get back to the original variable and get a reasonably nice result. We had obtained that integral of square root of 1 plus x squared dx is 1/4 hyperbolic sine of 2 times u plus u over 2 plus constant of integration c. And here x is hyperbolic sine of u. In order to return back to the original variable, we now expand hyperbolic sine of 2 times u using the double angle formula. Hyperbolic sine of 2 times u is 2 times hyperbolic sine of u times hyperbolic cosine of u. So 1/4 of that is just 1/2 hyperbolic sine of u times hyperbolic cosine of u, and then we have still plus u over 2 plus constant of integration. Next, recall that by the basic formula about the hyperbolic functions, hyperbolic cosine of u is a square root of 1 plus hyperbolic sine squared of u. So we get that integral of square root of 1 plus x squared dx is 1/2 hyperbolic sine of u times square root 1 plus hyperbolic sine squared of u plus u over 2. And in this formula, we may now return back to the original variable easily because hyperbolic sine of u is x. And of course, u is hyperbolic arc sine of x. So we get that the integral of square root of 1 plus x squared dx is 1/2 x square root 1 plus x squared plus hyperbolic arc sine of x divided by 2 plus constant of integration. And this is now our final answer. Integral of square root of 1 plus x squared dx is 1/2 x plus times square root of 1 plus x squared plus hyperbolic arc sine of x divided by 2 plus constant of integration c. In this example, we compute the integral of dx divided by square root of x plus cube root of x by the substitution x equals u to the power 6. Then dx is 6 times u to the power 5 du. The reason why this substitution works is that now square root of x is square root of u to the power 6, which is just u cubed, and cube root of x is cube root of u to the power 6, which is u squared. And this integral of dx divided by square root of x plus cube root of x becomes integral of 6 times u to the power 5 du divided by u cubed plus u squared. In the denominator, we may take u squared as a common factor, and that cancels out by a part of the numerator. And we get that this integral is 6 times u cubed du divided by u plus 1. Now here this integral can still be simplified slightly. The integral of dx divided by square root of x plus cube root of x becomes 6 times integral of u cubed du divided by u plus 1. And this is just 6 times integral of u squared minus u plus 1 minus 1 divided by u plus 1 du. And this we obtain by polynomial division. And now the result is easy to compute. So we obtained that integral of dx divided by square root of x plus cube root of x is 6 times integral of u squared minus u plus 1 minus 1 divided by u plus 1 du. And this is 2 times u cubed minus 3 times u squared plus 6 times u minus 6 times natural logarithm of the absolute value of u plus 1 plus constant of integration. We return back to the original variable. Recall that we substituted x equals u to the power 6. So u cubed is square root of x, u squared is cube root of x, u is 6 root of x, and we get that the integral of dx divided by square root of x plus cube root of x is 2 times square root of x minus 3 times cube root of x plus 6 times 6 root of x minus 6 times natural logarithm of 6 root of x plus 1 plus constant of integration. Here we were able to leave out the absolute value signs under the natural logarithm because the quantity 6 root of x plus 1 is always positive. So the final answer is integral of dx divided by square root of x plus cube root of x is 2 times square root of x minus 3 times cube root of x plus 6 times 6 root of x minus 6 times natural logarithm of 6 root of x plus 1 plus the constant of integration. In this video we discuss integrals of square root of 1 minus x squared dx and integral of square root of 1 plus x squared dx. The first integral was computed by the substitution x equals sine of u, the second integral by the substitution x equals hyperbolic sine of u. And these substitutions allowed us to get rid of the square roots in these integrals, and therefore they worked. The last example was integral of dx over square root of x plus cube root of x, and here we used the substitution x equals u to the power 6. And this substitution works because then square root of x becomes square root of u to the power 6, which is u cubed, and cube root of x becomes cube root of u to the power 6, which is u squared. Hence, by this substitution, we got rid of the roots in this integral, and the computation became possible.